All right, I am going to get started because according to this, I'm at time. Are we good? Yes. And I have quite a few slides to get through, more than I think I've ever had before. Some stragglers will come in. Thank you for coming. This is Declarative Style Evolved. It's a sequel of sorts to my 2018 talk. And we're going to see a bunch of stuff. First of all, some standard disclaimers. First of all, turning on my clicker, and then some standard disclaimers. The code you're going to see is all real. If it looks a bit strange in places, that's why. It's taken from open source libraries I work on as part of my day job. I have removed a bunch of syntactic noise, so in service of making it easier to read. So you might spot some errors. Assume that, all the things exist where you put them. Ask questions as we go. I'll either answer or defer them. Here are a few things about my slideware for those who are interested. All right, let's get going. Now, I almost never do about me, but just very briefly, I used to work in games. Then I worked in finance. Now I work in embedded. So it's been an interesting career. I work with Michael Case and Luke Valenti, and I strive for good code, and I achieve it sometimes. That's enough about me. By the way, this picture is not me. It's plausibly me. I wasn't born much before the Dragon Book came out. So.
There's a paperback of the Dragon Book?
I might have been born a few years before that. So why do we want declarative structure? What's declarative style about? It's about the first part of the answer of what is declarative style is hard to answer. But I'm going to try to give examples through the talk. And why is it good? Well, simply stated, I want to decrease the entropy in the code. This is a goal for software engineering in general. The best way I found to approach that goal is to adopt a more declarative structure. Now, I work in embedded. As you might intuit, I can't be declarative all the time. At the end of the day, I have to write bits and bytes. But as we'll see in this talk, I've tried to make the structure declarative to enable reasoning about where I have to be imperative. So in 2018, I talked about declarative style. I presented some code guidelines to strive for. Maybe you're expecting more revelations along those lines. I don't know. The truth is I can't tell you how to make everything declarative, like I just said. And I don't want to, because we shouldn't hammer C++ into any one mold, right? But what I can show you is ways I found to write good interfaces that support declarative structure and the composition of parts, right? And like I said, implementations at the very low level can't avoid being somewhat imperative, and nor should they. But we can make things nice just slightly above that. So I want to ask out the gate, what is C++ good for? What do you think it's good for? If you ask the internet, this is what you find. Performance, performance, performance. The typical domains are games, finance, fundamental systems, constrained systems. Now, C++ is good at performance, but to me, this is not the right answer. Because C++, let's face it, doesn't have a monopoly on good performance. Although we claim to leave no room underneath, obtaining the best performance is always hardware sensitive. It's always kind of finicky. And, Alex Stepanov said, if you write any compiled language as if it were Fortran, you're going to get within about 20% of Fortran's performance. So, what I think C++ is best at is the combination of these things. Firstly, interacting with hardware, layout control, low-level access. We have a memory model. Most languages don't have a memory model. They just inherit whatever LLM does, which is what C++ defines. We can do metaprogramming in a way that no other languages can, writing code at compile time so that runtime is efficient. In particular, variadic templates, which almost no other languages have, and many other languages fail to appreciate. I can't understand why some other languages are not rushing to obtain variadic generics. And this gives us the ability to build up abstractions and compose them without losing performance. So all of these things come together to make good C++. This is what C++ is good at. This is what C++ is world beating at, the combination. So I would go so far as to say that if I'm not using all these tools to the fullest, then I'm not getting the most out of C++. My personal experience is that especially over the last 7 years, I've worked in those kind of demanding, constrained environments that C++ is well suited to according to the internet. Low latency, low-level OS interaction, low-level hardware interaction, extremely memory constrained, compute constrained, all of the above. And yet, in that time, anecdotally, I estimate I've written 90% templates. It's rare that I write something which is not a template. And when it is, it's often just an empty struct, or occasionally a one-line inline function. And maybe 50% of those templates have been variadic. Now, this is just my anecdote, and it's not data, but this is what I feel. Now, I said this 7 years ago. I'm going to repeat it because this is a simple thing to state and a huge thing. Dijkstra said in his most famous paper, we should do our utmost to shorten the conceptual gap between the static program, the code, and the dynamic process to make the correspondence between the program in text and the process in time as trivial as possible. This is huge, right? What this is saying is like, if I can see 10 lines of code that does a job at the right level of abstraction, I can actually understand a few of those lines of code, right? If it's just in my vision on my monitor, and I don't have to hop around places, I don't have to mentally stitch together all those places that orchestrate things, then maybe I can reason about it, maybe I can make it right, maybe I can understand it. And that's what good declarative code is about to me. Now, to that end, recapping slightly on my previous talk, I'm trying to cultivate an allergy to statements. This is a goal. I mean, obviously I use statements, but my goal is to be allergic to them. So, we know that iteration statements oftentimes ought to be replaced by algorithms. Iteration statements belong inside algorithms where they are no longer raw loops because they're implementing the algorithm, right? Jump statements, I always feel bad if I have to put those in loops inside algorithms. It seems like there's a better way to do it. The only jump statement I like is return, which is not on this slide. And as far as selection statements go, they really belong ideally at two levels, either down at the leaf, inside some kind of class that embodies the choice, like optional, encapsulating that imperative part, or at a top level where we're providing a configuration choice to a user of our code as a mechanism of composition, right, to reflect some fundamental choice in components. So what's the real goal here? My real goal, like I said, is to decrease entropy. It's to provide flexibility. I want flexibility, I want malleability. I want to write robust software that I can extend to support new use cases because they're always coming along, they never stop. And I want to have well-defined places to plug in those new cases, to plug in those new components. And I want to be sure that the code is high quality, to be sure that everything is well tested and it works. Now, the code bases I work in have the following features in general at the moment. A lot of compile time use of types, right? Highly composition oriented, lots of metaprogramming. This despite the fact that I do very low level embedded work. Low level to the point where sometimes I get to change the hardware in concert with the software, or my team does anyway, to support certain use cases. So I'm on bare metal. I have no allocation. I have no such and such part of the STL. Think freestanding ++. I'm also highly constrained. So the total size of my binary, I measure in kilobytes. 95% of the code is dealing with I/O and a very small amount with computation. And yet, I'm able to use contemporary C++ to provide these abstractions. And much of my job is observing my team trying to solve problems and building up abstractions to help them. Now, there's lots of heavily templated code that I use. I want to preempt a boring question, and because the answer to this question is always the same. How are compile times? Always acceptable. Like all of you, I'm sure, I'm a selfish engineer. I want my workflow to be ultra smooth. I want the code to be perfect. Of course, I'll make mistakes. So I want the computer to be an instantly fast, perfect oracle so that no bugs ever leave my machine. That means iteration time is good. I want the productive workflow. Okay, so let me start out by talking about testing, because the declarative style implies compositional to me. So the goal of this really is testing, because it turns out that code that is amenable to test, code that is well tested, is well structured in general. So what does that mean? It's quite tricky. It's quite difficult to test well. It can be especially difficult when you're wrangling specialized systems that are not like your desktop environment, especially when you're in embedded. But it's an immediate area where declarative style pays off. The lesson I've learned hard is that testing has to be done at the right level. I want fine-grained testing, I want composition. And what happens when a certain level is easy, and by level I mean, well, I don't want to get hung up on terminology, but you can think of like unit testing, integration testing, system testing, whatever words you want to use to represent those layers. But there's clearly an idea that there are low-level tests that as engineers actually implementing features we should be responsible for. But what happens is oftentimes an organization will have a particular strength of testing in a certain area. You know, you have really good validation engineers, you have really good quality engineers, and they're testing at the level above the unit tests. And that level is really good, and it's really easy as an engineer to lean on that level of testing. And what happens then is we end up writing tests which bind more behavior than necessary, they're more brittle. They work, but they aren't decoupled enough, right? We're victims of testing at the wrong level, and we get these kind of effects. Increasing entropy, because we're humans, we do what's easy in Rich Hickey's sense of easy, right? What's close to hand, what we're used to. So if it's super easy to spin up integration tests, then probably what I'm going to see is a bunch of people spinning up integration tests to test things that really should be tested at the unit level. And sure, it'll work, but CI times will increase, tests will be brittle, tests will pull in dependencies, and problems will be hard to trace back to their sources. Dave?
Can you tell me what it means for a test to bind something?
I mean to rely on behavior that was incidental to the test.
Great.
That's what I mean. So when I say they bind more behavior than they need to, yes, you want to test one thing specific, you end up relying on other behavior. So here is a typical sort of high-level structure, of a layered structure of an API in the embedded world, right? So we might have at the bottom the stuff that does the actual hardware interaction. A level above that, we have an abstraction over it. And then we have some kind of control interface, which is exposing a lot of knobs. And then above that, we have a convenient interface, right? Unit tests at every level should not need to know about the APIs above and below. Those should be insulated. I don't want to be pulling in a 10,000 line file of register definitions in order to test the convenience interface, right? I just want to declare the few things it depends on in order to have that piece that I'm testing feeling like it's situated. I want decomposition of these APIs. Now, not only should testing be easy in C++, but it should be easy in the build system. This is like the first lesson I've learned. Again, if it's easy to test at a particular level, you get that in spades. And commonly the build system doesn't support things equally. So we need to make it particularly easy just to make unit tests. We want to shift that development left, right? To encourage good tests, fast tests, and good interfaces. Again, I'm a selfish engineer. I want my workflow to be ultra smooth, and I should get all of this stuff out of the box. I don't think that's too much to ask. And this isn't just C++. If you have Python or other things in your system, the same kind of that you need to test, the same kind of things should apply. And all kinds of tests should be just as easy to declare, right? It's not just about unit tests, it's about all these other kind of tests. Fuzz tests, mutation tests, property tests. Compilation failure tests are very important for me because I do a lot of template work, right? And nowadays it should be just as easy to take advantage of all of these, and indeed easy to take advantage of whichever unit test framework you like. There's several unit test frameworks around. It doesn't really matter which one you use. Whichever one your team uses is conventional, but the usage is all pretty much the same. And for 90% of testing, they're all as effective. So as with testing, so of course code quality in general should be automatic and it should be axiomatic to get with a one-liner in your CMake or build system, this stuff, right? Linting, formatting, coverage, all the quality. I don't want to spend any of my time doing any of this. I want this to be super easy so that I can just declare it and get on with writing the code. I don't want my team to have to spend time on any of this. This stuff should just come ready to use. Now, we want to make it easy to do the right thing. And global variables are a fact of life, to my life anyway. But they're still one of the primary evils. And of course they exist, but I don't have to like it. And I don't have to go along with the easy way of tolerating it. Declarative style demands that I feel this pain so that I don't blithely let entropy increase. So I want to make it hard to do the lazy thing, right? Which means that I want to do things like making tests random by default. And when and if I have a legacy system, it's quite likely that most of the tests won't be randomized and won't be able to be randomized for a while. Yeah, Michael?
When you say random by default, you mean run in random order?
That's correct. I mean to run in a random order, so that there are no dependencies between the tests, right? With global variables, with global state, that is a very, very common thing that you write tests, you don't realize there are dependencies between the tests. But all good unit test frameworks, which I think means all unit test frameworks you would think of, allow you to run them randomly. They don't make that the default, but the build system can. But it's likely if you're working in a system which has tests but is not sufficiently declaratively decomposed and recomposed, that you have problems with test randomness. So we want to make it noisy to turn off randomness. Like you can do it, but it's definitely something to be fixed. I'm not going to let you forget it. And this is a tactic for evolving poor tests. Obviously, some tests are better than no tests, and you're starting with some. But we just want to make it clear when things aren't good and why. Okay, so I want to make the desktop workflow efficient. Everything takes time. What I want is new code to be testable on its own quickly. And then it's also part of a subsystem, a system, the whole enchilada. Tests at each level roll up. If that isn't easy, people do what's easy. And that means entropy increases. So this is what I want from my build system. Now the corollary to this is that I believe the command line is the right place to situate things. And that's the simple place to situate things, right? And using a few tools like your toolchain, like CMake, like Git, but just a few, right? If you find yourself building bash scripts, wrangling environment variables, you're probably going down a slippery slope, because the more that the desktop experience gets away from the CI experience, and these things grow in an ad hoc manner, they aren't well documented, people lose familiarity with build tools, start to treat them like ancient runes, again, entropy increases. Next slide has a take. You can, again, decide the temperature of it. In my opinion, mocks are usually a code smell. Now, test doubles have their place, but too often I see the ease of use taking precedence over the desired structure, right? And so I see mocks like this. This is a callback. Why does it have 6 functions? For almost all tests, all of this is boilerplate. Mocks exist for objects. You don't want lots of mocks because they're boilerplate to set up. So what happens? Mocks encourage larger objects. LLMs do not help here. Here is a commit from a couple of weeks ago. This had no effect whatever on the function of the code. This was just removing boilerplate. Once people have mocks, they think they have to mock everything because we humans are copy-paste machines. We want to solve our problem and we see, oh, a problem has been solved that's quite like mine. Let me just grab that. And then I get all that boilerplate. We don't need it. Also, mocks just live for classical object-oriented style. And that's only one way of doing things. I don't want the tail to wag the dog here. I don't want the mocks. When I want to test something, I don't want the mocking framework to dictate that I'm using runtime polymorphism. That's not a suitable thing sometimes. And I don't want those kind of fundamental choices made for me just so I can do tests. The other thing that mocks do, or at least Google Mocks does, is it makes my tests unreasonable, right? In the sense that I cannot reason about them because I'm having to reason over time, and I'm reasoning about multiple things happening because the arrange part is mixed up with the assert part. The mock interface uses a builder pattern for ease of syntax, but it doesn't give any ease of structure or ease of reasoning. And over time, I have seen tests like this grow to 30 lines, 40 lines, 50 lines more, and there's no way I can understand that. It's too hard, I can't understand it. Instead, I want my test to look like this: arrange, act, assert. This I can reason about. This is just a few lines. This is just in my field of vision. This I don't have to temporally reason about. What Dijkstra said I'm no good at. And he was right. Okay, so who here uses mocks? Yeah, half or maybe more than half the room. So, maybe I'm wrong. Maybe I'm just holding them wrongly. But I would have to say that every team I've worked with also is holding them wrongly. And, maybe this is just what Google Mocks encourages, but maybe it's not all mocks. Whatever, it's only all mocks I've encountered in my career. So, maybe they're a poor solution for most tests. So the somewhat surprising point that emerges here is that I think tests... Sorry. Michael pointed at Matt pointed at Dave? Yes.
Okay. One thing I've found is that if you really practice generic programming, a lot of times what you end up with is a parameter that's abstract enough that you can put something that isn't what you would normally use in your program there and test the component that's using it. And a lot of times you can instrument that component.
Yes.
And that's much better than mocking.
Absolutely.
Partly because it gives you the concept that you're modeling gives you semantic rules that you have to follow that make sure that it's meaningful that you're doing the test on that thing.
Thank you, Dave. You've just articulated something which will be spread throughout the talk, I think. I'm 100% on board with that. Yeah, Steve.
Yeah, another thing with mocks, which I use and hate, you're testing your theory of how that other component works. You're wrong.
Right.
It's like, I'm wrong.
Right. So my sort of surprising point here, a point that I'm really starting out this talk with is that tests ought not to be declarative, because tests should be very small scale, right? They should be on the scale of our ability to reason. Do this, then do this, then do this. That's it. But it's declarative structure that enables that kind of small scale testing, in my experience. Okay. All right, any more questions on this? I'm about to move on to the next. Yes, Dave.
It's interesting to see the way you're using imperative and declarative together. You're saying tests should be imperative, but it's declarative structure. And usually imperative and declarative are in opposition. So can you say a little bit more about what's going on here?
Yeah, well, so imperative, obviously, I just says like, do this, then do this, then do this. If that's at the level of a few things, then arrange, act, assert, then I can reason, right? It's the declarative structure around that. It's the compositionality. It's the ability to inject things into my API. So my APIs are as declarative as possible, and that's what enables those tests just to be bang, bang, bang.
Okay, cool.
That's my thesis anyway. Richard.
Just a thought though, like, isn't the sort of larger part of what a program does is sort of arranges everything and then just runs a declarative structure? So it's basically like running a program except for the asserting it.
Yeah. So I think you're saying like, what would the ideal program look like? Well, main would say, declare this thing, compose it with this other declared thing, compose it with this third declared thing, and then go.
Yeah.
Right.
So you're really just adding the assert to it.
Yeah, I guess so. But I mean, are mocks that way? Do they mix arrange and assert? If that's desirable, then they do it in a way that I find is not that helpful. Anyway. All right, so I'm going to go through an evolution of logging. You can find this code. Well, a lot of the code is on. It's an evolution. So if you look at the head of this, you won't see exactly this code. But this is logging, right? Logging is imperative. But this is sort of a discovery of declarative API techniques to plug logging together to enable it to be, obviously, when you do a log, that's an action, right? Yeah, so this is a true story. So how it started. I mean, we had some kind of logging solution. It was similar to many. We're not programming 30 years ago. We have a perfectly serviceable framework. It does the job. So a few things I want to point out here. So the message that gets passed into log on line 2, that's actually a pair of a compile time string, your common or garden compile time string in C++20, and a tuple of runtime arguments. So it's a format string with the associated runtime arguments. SC on line 11, that's a little UDL that turns a compile time string or a string literal with a templated UDL. It turns it into a type that has those string characters in the type. Format helper does some compile time formatting there where it can. So we're trying to format things at compile time when we can. And then output line sends the line somewhere, right? Just stood out or wherever. FMT print in tests. And this is fine. So here's your common or garden string constant class that I mentioned. And the log typically would look like this. And because the name is a string constant, this would be able to be formatted at compile time. Wherever we can, we put things at compile time. And then at runtime, it would print this out. Okay. We had a good time. Things were fine. But more requirements, of course, were coming. One day, my colleague Luke has lots of good ideas all the time. And he's very excited about things. He said, you know what? I want logging to be everywhere. I want it to be super cheap. I want it to be ridiculously cheap and everywhere so that we don't have to think about it. I want it to be negligible in terms of performance. And this is actually really useful. This is very important for our validation engineers, our downstream testing, because, sometimes in embedded, printf debugging is what you get. So Luke has these ideas. So we write this other logging backend using the MIPI syst spec. It's you can go and look it up. It's a binary log format. And now we have 2 loggers, one for testing, one for real life. Okay. And we're doing this at the moment. We're doing if-defs. Okay. Well, the first thing to say is how do I test the binary logger? Well, okay. The binary backend ends up at this function. So I give it a destination, and then I can write a test destination which checks things that it's expecting. So I abstract this idea of a log writer, and I can log something and then check that the binary output is correct. That's okay for a while. Now, I told you my total space available is measured in sort of kilobytes. And I want logs to be everywhere. So you might be thinking, where do all these log strings live, right? Even if I'm doing the formatting at compile time, if the strings are in the binary, they're going to take up tons of space. And so this is how the guts of logging work in our system. So the source code's at the top. When you log hello, that's the type, right? We put it in a type. We have a catalog ID function declaration, a function template declaration that needs to be specialized for each of those types. But we don't specialize that up front. We build the lib, and then we use nm to pull out the undefined symbols. We use a Python script to process them into JSON and into the C++ specialization for that type, which is now just returning an ID, right? So we're using the Python script to assign IDs. Then we compile that, we link together with LTO, and now the logging, when it happens in real life, just outputs an ID. And a script catches it over a connection and reconstitutes the human readable log from the JSON. Everyone clear? Good. This isn't like a technique we made up. I think several people have had this idea over the years. It's fairly standard, I think, by now. So back to this. This is how we did it for a while. I didn't like it. I wanted a way to, and I didn't really, because I don't like having if tests, because I don't like if statements, right? This is a statement in the code. This is a selection statement. This is going to be brittle. So there are various ways we can do this, right? We just saw conditional compilation. I don't like those ad hoc conditions. Neither here either. We could link different implementations, but that's just shifting that condition into the build system, right? It seems like the wrong thing to do. Runtime polymorphism is out for us because of performance. Now, I know oftentimes people say you shouldn't bother much about virtual functions, it's not worth optimizing. Well, if you're unembedded, it is, because I don't have any cache, right? I barely have a branch predictor. I don't have a superscalar architecture which can hide virtual functions. And the logs need to be everywhere. And if a log goes from 2 instructions to 5 instructions and it's everywhere, it's kind of a big deal. So the one thing left to me is compile time polymorphism, right? And this fits in well with my code base. So what I'm going to do is use the global API injection pattern. It's just the ticket for things like logging, and it lets us keep things inside C++. So here's how it works. Let's start by defining a null logger. Does nothing, but it does it with style. Check out that auto-ref arg pack. Okay, so we have a variable template which is gonna tell our program which logging implementation to use, right? So the log config is where we select what to use. By default, it's the null logger. And this is great for tests because most tests don't care about logging. Most tests that I want to get rid of do actually care about logging, but shouldn't. So I want to remove that boilerplate. And then the log function, this is our global API, right? What does this do? Well, dummy args here is always going to be empty. It's always going to be an empty arg pack. Nevertheless, we use it to select the specialization of log config, right? This is going to tell us which logger to use. And as long as we give log a return type, here we give it void, the compiler doesn't need to look inside this function body before we provide a specialization, right? So everything's going to work out all right. Templates are the only thing in C++ which lets you kind of use something before you've declared it, right? So we're going to specialize it at some point. The compiler doesn't need to know about that when it sees the body of log, because it doesn't need to look inside the body to figure out what it returns. Now, a couple of techniques about packs here. There are a few ways to wrangle them. I'm using one of them, but there are a few ways we can do it. You can have a nullary function and you can give it explicit args, and they will all go into the X's pack, and T's will be empty. So that's one way to do it. Or you can put a pack in between 2 deduce types, and that's also always going to be empty. Just the way that deduction kind of makes the types come together. So we have a bit of latitude in how to structure the arguments to achieve the right result. And there's another way you can have some explicit types followed by some deduce types, and you're going to separate them that way. So there's a few options here. So this makes me confident that if things change, if I need to support new things, I can still make this work. Well, now we have our 2 loggers, the format logger and the binary logger, and they're implemented in the way that they're implemented, however they're implemented. And we have them both declared in the program, right? But we're only ever going to use one of them, because here's the crux. we specialize that variable template to tell the program which API, which implementation we want to use. And for any given binary, we need one, and only one. So every translation unit has to see this same specialization to avoid ODR violations. But that's okay. That's okay for global APIs. And in our code, we only have a couple of translation units anyway, because we only want one logger at the moment, asterisk, bear that in mind. So tests use the format logger where they need it, the null logger without any fuss where they don't need logging, don't need to test it, and real life we use the hardware logger. Yeah, so this is what a test looks like that doesn't care about the logger. It doesn't bother to mock anything, it doesn't set anything up, it just tests what it wants to test. It gets the null logger. Now, there are log statements inside the callback and that happen, but they just go to the null logger. The test doesn't actually care about that part. Doesn't need to bind that behavior, right? Doesn't care about it. So the default for almost all tests is now they just run quietly, and that's already a win against some boilerplate. Tests that do care, they can inject a format logger and they can direct it to a string. And then they can catch whatever comes out and they can actually say, well, this is what we're expecting. That's also nice and easy. Any questions? Yes, Patrick.
Do tests that care about testing logs and tests that don't care have to be compiled separately?
The tests that care about testing logs and tests that don't care have to be compiled separately. No, because tests that don't care just don't look in the log buffer. It doesn't matter where the log goes. Like they could use a null logger, sure, but they're not going to look in the log buffer. And typically you would clear the log buffer in your test setup, like your framework provides or something like that.
Well, then let me rephrase it. Do tests that care about logging but want to do test logging in different ways, do they have to be compiled separately? Because you have this global specialization.
Yes. If you had the situation, I haven't had that situation.
Okay.
But not in this situation. But yeah, it does sometimes happen that you want to set up a particular thing to do one test, and set it up another way and inject it to do a different test. In that case, they are two separate test binaries.
Okay.
But in my build system, it's super simple to declare a new test binary, so that's no impediment. Richard.
Okay, so if I understand correctly, the idea is if you had multiple translation units, one of the translation units, one of them has to define this. And when you say the test can choose to do it, it's choosing to put that declaration somewhere.
If you're going to define this, every translation unit that uses it has to see the same one, or you get an ODR violation.
Right.
That's the sharp edge here. That's why I only use this for global APIs, but it is super useful when you have global APIs. Okay, where were we? Yeah, so we were here. So life is good. We have tests. We have tests that do the right thing. We have tests that don't care, get rid of a bunch of boilerplate. And we use your various log macros for the various severity of logging. And life is good. We carry on. Okay. Next thing that comes up is, actually, there's not only one logger because we want to do secure logs as well as insecure logs. Okay, this happens a lot, especially in embedded. You think you have one of these things or two of these things or three of these things, and actually it turns out you have n of them. Life hits you upside the head with these requirements. Well, okay, actually we can deal with this. Because this log function, we can just flavor it with a specialization, right? We can just add an extra type in there, which becomes the way we specialize our log config. Now, the dummy args are still empty. We just have tag types there to say, I want to use this for regular logs and this for secure logs. Yeah, you have what you think is a global API. You fiddle with the injection pattern. Now you have two global APIs. Now, that's fine. The calling code is getting a bit worse because now we have trace, info, warn, error, normal, and the same things for secure. I guess I can convince myself for now that we'd need these anyway. This would be the same for any old logging system, right? It's no big deal for now, maybe. It's a convenient interface on top of a pretty nice mechanism, so I'm fine. Okay, so things go along for a little while. Okay, now someone says, oh yeah, we looked at the MIPI SysT spec and we can pack all these other things into the binary packet, like the module ID, because logs belong to a sort of module of the code. It turns out you can stuff all sorts of useful things. So, okay, so now I think, what am I going to do? Am I going to add the combinatorial explosion of the macros? Probably not. Am I going to squeeze in positional parameters? I don't like it. So arguably, the best time to make an abstraction is when you have one thing, right? But it's really hard to recognize that. So at least I feel bad about it. So the second best time is when I get hit by the second thing, then I make the abstraction. So I want to be declarative. So I think, well, you know, code that lives together mostly uses the same module ID. So let's declare the module we're in. I don't want to have to put the module in every log call. I just want to declare it at scope. And the code that lives in that scope is mostly going to want to use the same module. All right, let's do that. Let's define a default, right? We've got, so a module ID we name with a compile time string. And by default, we have a default one, right? This is a global scope. And then we define a way to declare a new one. And then I have the existing macros pick up that type. So they know the module ID string.
Is that maybe unused on the right place?
Yeah. Yeah, it's strange, I know, but that's where you put maybe unused for type aliases.
Okay.
Why does it need to be there?
Well, this is just saying that, well, I think it needs to be, the truthful answer to why it needs to be there is because I got a compiler warning without it. So it's possible that you could declare a module but actually never do a log.
Okay.
In that case, it would be unused, I guess.
Gotcha.
Okay, so we have this situation. Like I say, logs from the same physical place in the code pretty much want to use the same module. So we can declare it at namespace scope, we can declare it at class scope, we can declare it at function scope or at block scope. Now, in reality, I have to turn off warnings about shadowing declarations, but this is what scopes are for, right? So I don't mind doing that. Okay, so life is good again. I don't have a lot of code that's gumming up log sites. I have declarative modules. I have good test structure, because tests, of course, can declare modules and then check that they came out right. Some constraints here, which are generally for my use case, is that all that log metadata, like the severity in the module, is always known at compile time. That's just part of my system. Okay, but now I get a request from another team. Because it turns out the way we implemented the back end of the binary logger makes a choice about the packet it sends based on how much data. Because if you don't have much data, you can just send a really small packet. If you have more data, you have to choose a bigger packet type in the MIPI spec. And it turns out that baking that choice in was not a good idea because we want to control it, because we don't want to give up the module ID just because we didn't have any runtime arguments to format, right? For example, yeah, we still want the catalog message in that case. Okay, so what the binary logger, what does it do? Anything that can be formatted at compile time, we format at compile time. Remaining format string we convert to an ID, and then the backend sends a packet with the remaining runtime format arguments. That means for this log, there would be one compile time argument and one runtime argument, right? And it would look, something like this. The log, we get the compile time formatted string with its ID. We get the runtime argument. We send a packet that has some header, then the ID, and then some data, right, which is the runtime arguments. So the binary logger does these three things. It builds packets, it assigns IDs, it sends the packets. So ideally, I want to separate these things out. And I want to give the user choice over which packet type to build and send. How am I going to do that? Well, I had implemented senders the year before. Senders use environments the receivers communicate with the inside of the operation state onion by providing this environment, which is a key value store. So I thought, we have a declarative module ID. Why don't I extend that to a declarative environment? And actually, my environment is simpler than the sender style because I don't have to worry about runtime arguments. So my environment is completely compile time. So the simplest form of environment is just the single key value, a property. And it has a query function. And when you query it, it returns its value. And you query it with its query, it returns its value. So this is one key value pair. I got the idea from senders. Now, when you put together several environments, you get an environment. Same interface, query, right? So we pass in a bunch of environments to an environment. As long as it's a valid query for one of them, that's what that constraint is, we can query it. And we find the first environment that responds to that query, right? This means that because we're finding the first one, this means it's going to be fairly easy for us to override key values by just prepending environments into our type.
Oh, that's cool.
And then nth t is, your favorite way of getting the nth type out of the pack. In C++26, that would be pack indexing probably. But we're not on 26 yet, which is why it says nth t. And then we run the query on the environment. And the query looks like this. Bunch of code I know. I've actually removed some. But basically, it has a function call operator, which if the query responds to the environment, if you can query it, or rather, if your t is the environment you're passed, right? So you're going to call query on that environment passing this type, right? And in the case that the environment doesn't have this key in it, so this query is not represented, you can default and fallback. Notice the requires true. These two functions have the same precedence of overloading because they both have forwarding references. The requires true makes the top one more constrained for that case. Patrick.
How come you prefer prioritization over ambiguity?
Can you explain a bit what you mean by that?
You have an order that you search for the first one that responds to the query. Why do you prefer that over an ambiguous?
Why don't I want it to be ambiguous? Mm-hmm. Because, well, think of how module ID works, right? If I'm going to have a query for the module ID, but I'm going to be able to override it in closer scopes, right? Mm-hmm. So the environment that exists at namespace scope, I'm going to override that with an environment that exists, say, at function scope, and I'm going to add in a new module ID. I'm going to prepend the module ID so that it takes precedence over the existing one.
Really cool.
That makes sense.
Yeah. Good models, flexible scope.
Queries look like this. We covered that. So the default environment is empty, of course, because the query now controls like whether we want to provide a default value. And with a bit of metaprogramming, we do something like this. We say extend the environment with a new query and value. And now the module declaration works by declaring a new environment. Everything's just compile time. There's no code here. This is just a type declaration.
Because, previously, about 5 slides ago, you were talking about how you had to disable warning because of shadowing variables. Is that removed with this?
No. The shadow warning is still there.
Oh, okay.
But
It's about a type
I
rather
actively
than
want to override something in a more enclosing scope. Right? It's like shadowing's what I want here because that's what scopes do for me.
Yep.
Okay. So with this environment, I can actually now use it to customize everything. So even things which you would think don't vary or vary per call, there's not much reason for me not to put them in the environment because there's no runtime cost to it. So this environment is kind of an alternative way, a declaration-based way to pass arguments into my log function, if you like. Including some things that I don't actually need to know about, right? So the format backend doesn't care about the packet builder. The packet builder is still in the environment for use by the binary backend. So this is kind of a classic hourglass style pattern. the client code, if you like, can arbitrarily provide keys and values that the backend understands, the backend corresponding, because you plug in, the backend you want. The middle library code, whose job is assigning the IDs, doesn't care about any particular queries. So these environments just contain any old thing. It's all at compile time, and there's this nice pattern. So yeah, so the library code uses a builder that it picks up from the environment. Actually, in making these slides, I realized the writer could also go in the environment, but it's real code. The writer is not currently in the environment. It's just provided as a template argument to the logger. So yeah, this environment idea is a really powerful abstraction for this use case. So yeah, the library code uses the builder and writer that are customized. The client provides them, and now the client code can customize any part, right? There can be custom queries which the backend can pick up. There can be a custom writer. There can be a custom builder. If you want to replace the whole logger, you can still do that, right? Because you just need to provide something that provides a log interface and specialize the template to point to your whole implementation. And this, yes.
Yeah, so you've effectively made like the sort of type environment so that code can look up a type depending on a key. And
exactly, yes. Wow. And there's a bonus feature here. There's another thing which I didn't mention, but logging is, because we want it to be cheap and everywhere, it's extremely susceptible to inlining decisions, and indeed outlining decisions at various levels of the call hierarchy. And in order to deal with that, like, I don't want to put force inlines into my library, right? Allowing the client to override selected parts means that they can make decisions about inlining. And that's super important as well, especially when you have binary size limitations. Yeah, I don't want to be hard coding those inlining decisions into a general library, right? So now we've separated out these three things. And of course, the library provides out-of-the-box defaults. There's an implementation of MIPI logging. There's a packet builder for it. There's a format logger, etc. But the clients can override any part. And that is the story of how logging evolved to be a more declarative API. Does anyone have any other questions before I move on? Patrick.
There's more of a thing I noticed that's really nice with the types. Because you're using types instead of values to build the scopes.
Right.
The nice thing that you get is that you can't do this module multiple times in the same scope. That would be an error.
That's right. Yeah. It's an error to declare the same module multiple times in the same scope. Yeah. But that, like you say, that's actually nice, I guess. Okay. Now we've got logging. Now we have to also think about dealing with the unexpected, because one of these logs is not like the others. I'll give you a clue. It's that one at the bottom. Sometimes things go irretrievably wrong. This is bad. But all the top four logs here, they log, right? They log. The bottom one wants to log and do something else, panic. Now, to be clear, if a panic happens in my code, it's probably bad. That's when you see the computer just reset immediately. Doesn't even blue screen. So I don't want it to happen, but I do want to test it. So yeah, this is what log fatal does. First of all, it logs, then it panics. Well, guess what I'm going to do with panic? It's a one function global API. Guess how I'm going to test it? I'm going to inject it, aren't I? So I'm going to have a default panic handler, which does nothing with style. I'm going to have a variable template, which is the default panic handler. And then I'm going to allow people to inject their own panic handler and call panic, which will pick up the right specialization. Again, same pattern I used for injecting logging. And this time there really is only one panic handler. I'm pretty certain, there's not normal and a secure panic handler. They both just panic. Panicking comes at the end of everything else interesting. So it's pretty much the end. So, okay, so we're pretty much there. There are a couple more nice to haves that make logging call sites better. One of them is that, of course, const expr values that you have lying around have a nasty habit of becoming non-const expr when you pass them to functions. And I don't want that to happen. I want them to stay as compile time values. This also, cx value macro does that. Also solves the problem that there are some perfectly usable const expr values like string views that can't be passed as template parameters because they're not structural types. We had various ways to do this in the code before cx value. We had effectively things like integral constants or UDLs that do things like integral constants in the manner of P2725, that paper. But they've all been replaced by cx value, which does the job. Another thing cx value does is it's really convenient to treat values and types the same. When I log, I just want to log a type and I want it to say the name of that type, right? So yeah, so cx value does both things, so it's a sort of one interface. Okay, that's the end of logging. Let's change gears now. Let's talking about composing, and I'll give you some time to wonder how that works, but we'll cover it in an epilogue if we have time. Let's talk about composing asynchronous functions, aka senders. Senders, what do? Before senders, these three things are in three different places in the code. We send a message. We store the sent ID somewhere. Somewhere else, we get a callback. In that callback, we have to recover the state, recover the sent ID, store the response somewhere else. Later on, have something else process it. The shared state these things use to communicate is in different various places. And the major part of managing the behavior is managing that state, right? These things are forming an incidental algorithm with a corresponding incidental data structure that's spread over the code. Now, senders turn this state of affairs into this state of affairs. It enables us to declare this computation in one place. And also, the state flows through this computation in one place. We don't have to reason about how it gets stored and retrieved. It just passes through this computation as naturally as if we were passing values to functions, because that is what's happening. The program's no longer spread out in space. Remember what Dijkstra said. If I can see this in my field of vision, if I can reason about this, I'm much less likely to make a mistake. I can see this just as if it were regular function calls. I don't have to reason about things happening over time. It takes that time and puts it in a small space. So senders abstract away the details of handling the concurrency. And they let us concentrate on expressing this computation declaratively. The details of dealing with the mechanism of concurrency, we don't care about those. They don't get mixed up with our business logic, what we're actually doing. And that's one of the great things about senders. They don't care about the mechanism of concurrency. This same thing I can run on threads, for example, in a test, or on interrupts, for example, on hardware. We have separated the idea of what we're doing from how we're doing it. This is cool. And this, to my mind, is the real power of senders, because in a sense, anyone can write an asynchronous framework that makes good use of their large-scale concurrency and parallelism. The real power of senders is you can shrink that all the way down, and it supports very small, very constrained devices at least as efficiently as if I would handwrite the code myself. Am I right, Dietmar? Well, embedded processors don't tend to have much parallelism, but they have concurrency in spades. Everything is happening on interrupts. And the reason this is important is because of my next slide. This is approximately a diagram of the number of embedded processors in the world versus the number of desktop and server processors. Desktop and server processors exist. They don't show up at this resolution. You might think I'm joking, but the fact is, Actually, it's fairly rare right now. I don't have many embedded processors on myself. I just have some in here, maybe some in here. Normally, I would have half a dozen credit cards. I might have a health tracker. My watch doesn't actually have any processors in it, so that's something. But every desktop and server processor has dozens of embedded processors inside it these days. And that's not even counting, the ones on the motherboard, in all the peripherals, keyboard, mouse, etc. And that's just at my desk. I recommend trying to count the embedded processors in your house, or just in one room, because you start out, you're like, okay, microwave, oven, dishwasher, rice cooker, digital thermometer, tea maker, food processor, timer, Google Home, smart light bulbs, headphones, Bluetooth speakers. It goes on and on and on. And that's just the way of the world now. So super, super useful that we can run senders on these things. Okay, these things run by interrupts. And there are basically three kinds of interrupts. There are priority interrupts. They represent what you expect. There are timer interrupts. Also, they represent what you'd expect. And then there is every other kind of interrupt, sort of ad hoc interrupts that occur in response to us, like sending something and we expect some kind of interrupt back. Now, in my implementation, I have priority scheduler, timer scheduler, but the really absurdly useful one is the trigger scheduler. And the trigger scheduler allows me to do code like this. Now, I wouldn't call a bear connect and a bear start in real life, but this is kind of the action of trigger scheduler. So we can name a trigger scheduler, and we can say start a sender on that scheduler, right? And then the idea is that when an interrupt comes along, and when the ISR runs, it will call run triggers. It will call the associated trigger scheduler, which will then run the sender and allow that computation to proceed. So the compile time init build library, the machinery inside there for dealing with interrupt handling, is the mechanism of concurrency. And a lot of times what it does is hook up a run triggers call inside an ISR. Now, where this really shines is another combinator that I've called incite on, right? So what this is saying is we're going to send a message that is going to incite the next part of the chain. We will continue on the trigger scheduler that the send message caused, and then we'll carry on down the chain. And then inside the interrupt, so when we send a message, it goes away. Sometime later, an interrupt comes back, which calls run triggers, like I was just saying. Then the sender chain continues. Now, why do I have incite on? Now, this important point. Now, there's continue on in the standard, right? This is documented. This would be wrong, because as soon as I send a message, the hardware's off and running. Hardware doesn't care about me. Hardware's parallel. There's now a race between that message coming back and triggering the interrupt and me setting up and calling start on the next scheduler. Yeah, is that you, Steve? You just said, oh. Richard. Yeah, if I continue on, then the trigger could come back before the trigger scheduler has been set up to handle that callback, right? And so I need, this could be carefully done with when all. It's true. You still have an ordering dependency about which one you start first. There's basically a sharp edge here if you don't have an easy way to do it. Okay. So on top of senders, there's another library we have. It's called Groove for historical reasons. It's an open source library, and it uses senders as an interface to register operations. Now, when I say register here, I mean in the embedded sense, it's really a memory location with some special semantics. It's not a processor register like RAX. Now, we define things by saying, well, there are fields. We put fields together into registers, and registers have, registers and fields both have types, typically uint32Ts. And then registers we collect together into groups. And associated with a group is a bus. Bus is the thing that actually does the writes and the reads. Groups bring together registers that share a bus. Registers bring together fields. This is how we talk to hardware. Is this clear? Okay. The write and the read functions of the bus both return senders. Some buses don't have like remote things to do. They just have memory mapped I/O. It's just like accessing a regular memory location. In that case, they still return a sender, but it would effectively just do the thing. It wouldn't be asynchronous. It would complete synchronously. Or other buses can read and write across an asynchronous device. And in that case, obviously, returning a sender makes intuitive sense. Some buses can optimize the access to their fields based on masks. That's not too important for this talk, but it basically means that so if you have like read-only bits inside a register and you tell it you want to write the non-read-only bits, it can optimize a write because it knows that it doesn't matter what it writes to the other bits. It's that kind of thing. So buses can optimize things on that basis. Yeah, and buses can know things like if the underlying fabric supports byte enables, if some fields are read-only, like I said, if there are various different semantics. So if you've programmed the RP2040, which is inside a Raspberry Pi Pico, they have a very nice thing where there'll be a register at some address, but if you read or write to the same, if you write to the same register an offset from that address, you'll get an XOR of the bits instead of a simple write. So there are semantics like that that occur in embedded devices. Byte enables is for something like, say you have a 32-bit register, but you're only writing the bottom 3 bits. The bus might just allow you to send that byte across the bus instead of the whole 32 bits because it's a byte-enabled device. And all of these things are in service of avoiding a read, modify, write, right? If you can avoid at a higher level doing a full read, modify, then a write, if you can optimize that at a lower level, that's why all this stuff exists. Okay, this is what, so obviously sometimes you do need to do a full read, modify, write. This is what it looks like with Groove syntax. So we're saying the just here is just, we're going to address this register in this group. We're going to read it. That read is going to give us back spec. We're going to index into that spec and just XOR the byte on that register, return that value, and then we're going to write that value back. So we're reading it, modifying it, writing it. Now, we might have a bus. This might be a bus, right? This is a simple memory mapped I/O bus, right? So it's not doing anything fancy over the whatever fabric. It's just reading and writing to actual memory addresses. And it's just returning. So just result of is like just followed by then. It's just a way to make that computation lazy so it happens when the sender starts and not when the just is defined. So this bus is just doing normally addressable memory. It's not an asynchronous access. And we're going to do a read, modify, write. Now, what's the question you all have? Actually, it's at the top of the slide. The real question here is like, when we're doing memory mapped I/O, this looks like a lot of stuff, right? Why don't we just do star address equals value or something like that? Patrick?
One thought I had in mind was network on chip.
What about network on chip?
Like it's asynchronous, so you have to wait for the read or the write to
Yeah,
occur.
exactly, which is why we have the sender interface. Yes. So this same interface works for network on chip or for memory mapped I/O or for anything in between, sort of thing, right? But the big question is like, is it efficient to do this? This looks like a lot of code. Well, I'll put you out of the suspense. The simple answer is yes. It's as efficient as possible. If it were not, I could not use it. It's that simple. This code compiles to that line of assembly. In this case, it's because the compiler can see data. But if I make data like just a pointer to somewhere, then we see, read, modify, write in assembly. You see like, instead of one assembly instruction, you see 2 or 3. But you don't see 1,500. Now, if this is really, so this is a memory mapped IO bus, that's great. That's what I want. That's what I need, right? I cannot use it unless that's the case. Now, there is a bit more involved if it's actually asynchronous, right? Because then we have to deal with asynchrony. We have to use things like atomics. But we don't get more than we would have to handwrite anyway. So this senders-based interface is great. It offers all of these things. We get the code in one place on the screen and the data flow in the same place. We don't get to worry about the mechanism of concurrency mixed in with what we actually want to do. Most times I don't really care which interrupt is going to come back on, or I don't care whether the register is memory mapped or if it's remote. It's the same interface, whichever thing I do. It's expressive, it's declarative, and it's at least as efficient as if I would handwrite it. And if I had to handwrite it, I'd probably make mistakes. All right, let's talk about how to test concurrency. First. Because the truth is that almost all of my job involves handling concurrency of some kind, and it's interrupts. And desktop tests don't have interrupts, really, you might have noticed. So how do I test things in a way that works? Well, basically, I have two low-level primitives that I can use on the platform. I can turn off interrupts. That's like having a global critical section. Or I can do a very limited form of atomics. Basically, I get exchange of a 32-bit integer. So I don't have parallelism going on, but I have tons of concurrency. I don't have standard library things like mutex. I have a very limited atomic. So I can write a critical section RAI class, where it turns off interrupts, turns it back on again. That's fine. That's kind of the sledgehammer that I have. At least it has something going for it. It is super cheap.
Just to confirm here, when you say concurrency in like an embedded system, you're like, it's not like a multi-threaded bare metal thing. It's more about the interrupts could come in at any time.
That's right. So when I say parallelism, I mean having multiple threads at the same time. Like data races can occur with parallelism. Yeah. Because literally you have two things running at the same time. Yeah. Concurrency, on the other hand, is multiple jobs running at the same time, interrupts interrupting you. You don't have more than one thread, but you have concurrent access. Okay, so how do I write code that I can test and that is good, let's say? Because I have some problems. If I just have this one sort of sledgehammer, I could have things like this, right? These are two totally unrelated pieces of code. They use a global lock. And now, maybe they want to do this on platform, but this is not very good for a test, right? We wouldn't normally suggest to people, yeah, if you want to do multi-threaded code, just make a single global mutex. It'll be fine. I also have the problem of brittle correctness, right? Which is that if people forget to use these concurrency guards, their code might succeed anyway on platform because it just happens that they're running at different interrupt levels. One cannot stomp over the other. And today, because we have lack of parallelism, which might not be true for all time, right? Because computer power is getting faster and better in the embedded space all the time. So this accidentally succeeds, and I don't want things to accidentally succeed. I also have things like the implementation details here leak from critical section because it's like having a recursive mutex. And I don't know about you, but I always find recursive mutex is not very tasteful. So I could, in a test, I could implement a single global mutex, but I don't want to do that because of all those problems, because accidental success and brittleness. What I want is an interface that I can use identically on platform and on desktop, whose implementation can be selected appropriately. That's a clue to what pattern I'm going to use here. Forces reasoning about concurrency and won't accidentally succeed. So I'm going to use the global API injection because that's what I need. And I'm going to use call in critical section. So this takes a lambda or a function, and it calls it underneath a lock. Notice this time I have a dependent return type. It depends on the argument. It doesn't depend on the dummy args. So I still get what I need. The compiler still doesn't have to look inside the body. Everything's still fine. But I've still got, my injected policy and my selection of that. And of course, the standard policy is just going to be using mutexes, because that's what I have on the desktop. But notice also I have the first template argument here is a unique type, which I grab by just taking the declarative of a lambda. This means that every call site will have a unique type by default. But what you can do is, in your data structure which is protecting something, you can declare just a type, and that effectively becomes your mutex. Now, you still only get one per type, not one per value. So it is not quite per value, but it's not as bad as global. And you get to reason about using your mutex, which is what I want, right? Because this is going to be more future-proof than accidental success because there was just a global lock. So, of course, tests just use a regular stood mutex, and away they go. They use just regular locking code. The platform policy disables interrupts with some RAII type. It's still a global lock because that's all we have. But these now work the same at the call sites, and even better, what's happened is that I've taken race conditions on hardware and I've turned them into data races in tests that can be detected by thread sanitizer now. By introducing more constraints, by making it so that people have to reason about what they're locking and not just rely on accidental success, I've also enabled desktop testing, which actually has teeth, right? Because if you can run thread sanitizer, it finds bugs that you have no hope otherwise of finding, pretty much. So, because, on a single core platform, we don't get data races, but we can still get race conditions from concurrency. And so what this has done is provided the same API in tests by that decoupling, and it's turned those into test data races that thread sanitizer can diagnose. Okay. Another problem I have is stood atomic. It isn't really well built for embedded devices. If I say to you, what does stood atomic do? What do you think, right? What do you understand by stood atomic?
What's T?
Int. What do you think would be the assembly?
Assembly code instructions, the exchange.
You would expect atomic instructions, right? Stood atomic confuses the implementation with the interface, right? People use stood atomic when they want atomic instructions. But if they don't exist, what they actually need is atomic access to the variables. Instructions don't matter as long as they're efficient, as long as they uphold the C++ memory model. It doesn't actually matter if I get atomic instructions or if I turn off interrupts and use a memory fence.
Oh.
And this matters because I don't have atomic instructions very much on embedded, right? I'm very limited. Like I only have exchange. I don't have fetch add, right? I have alignment requirements. I have a ton of stuff. So yeah, if I do this and I forget to align my atomic bool, I'm going to get a processor exception. If I do this, then I'm going to get the right atomic instruction, but that instruction only works on 32-bit values. It's going to clobber something else whenever it does that exchange. These are things that my toolchain fails to diagnose. And this might be a problem in the toolchain, but it's also a problem of the atomic interface. And yes, as I said, I don't have fetch add. If I do this, what I get is that stood atomic is really trying to be atomic, really trying not to, like it doesn't know about interrupts. It ends up calling some function my toolchain provides, which does, I don't know how many assembly instructions with a loop in there, trying to do the atomic fetch add. But it would be a lot cheaper if I could just turn off interrupts, do the thing, turn them back on, right? A lot cheaper in some cases. So what I want here is for atomic to mean something for the interface and not the implementation. I don't really care if it uses atomic instructions on hardware. Like, there's a use case for lock-free and atomic instructions, but that isn't what the interface of stood atomic means to me. And as long as it upholds the C++ memory model, as long as it actually provides atomic access, I don't care about the instructions. I care that the instructions are efficient, not that they are atomic instructions. So, of course, I have an atomic policy, and I have global API, which do atomic operations. And the defaults are that they just call through to the atomic intrinsics which the compilers provide, right? Which do the, on x86, on desktop, they do the right thing. I cut out the memory order here, by the way, because of noise, but you can imagine that it's just passed through to the intrinsics. And then when I want to have an atomic T and I exchange it, I call through to the atomic policy. It's fairly easy to write an atomic T that just relies on the underlying things. And on desktop, it uses real atomics, if you like, and on hardware, it does what it can do. Probably exchange if it's available, and interrupt lock if it's not, because again, it's going to be a lot cheaper. And I can inject the types so that when I declare an atomic bool, I will get, actually, because atomic bool is not supported, the only atomic thing I get is a 32-bit integer. So a bool kind of, it will provide the interface of bool, but under the hood, it's implemented in terms of 32 bits. And that means I don't get, clobbering of other values. I get the correct alignment. Nobody has to remember to do these things. Things just work. So bringing all this together, what I have is a declarative interface for the build system. So it's easy to make tests that operate at the right level. I have a declarative interface for test injections so that I can remove boilerplate from tests. Only tests that care about I/O can actually test it. The rest can just test whatever they want to test. Senders give me a declarative interface for asynchronous and synchronous code alike. The code is in one place. I can reason about it. The data flows through it. I can reason about it. And it's as efficient as it can be if I handwrite it. And I have some declarative interfaces that deal with hardware limitations. I get to express the logic of the code without having to care about the idiosyncrasies of the platform. So yeah, testing at the right level is key. All of these things you would think of as non-declarative benefit massively from these kind of interfaces which allow those tests. Injecting global APIs, you saw it several times, 3-4 times in this presentation. I found it super, super useful. I use it in a bunch of places, as you can see. And code that is physically close makes for easier reasoning. So this is what good declarative style, good declarative structure gives us. Thank you very much. Now, do you want to see something kind of gnarly? I have epilogues.
I'm guessing that macro with the type and value. Yep.
Yeah, so if I do this log, I get 42 has type int. Now, you all know how to get a string from a type, right, with pretty function or whatever tricks, right? That's not the thing here. What I want to do is this, right? So I want it to work for x. 42 is a perfectly fine structural value you can pass to a template. A string view is a perfectly fine const expr value, but it's not structural. You can't pass it to a template. And a type, well, I want that to actually produce a type identity value, which I can then do something with, log or whatever, right? Now, I always know this argument at compile time. So what's this CX macro going to look like? Well, firstly, it's fairly obvious that it has to be a macro. So let's kind of write the skeleton here. We're going to do an immediately invoke lambda with some if const expr inside it. So we're going to basically want to see, did we get a value here or did we get a type? Okay. Well, the only thing I know of that can detect this difference is a function overload, right? You can't redeclare a class template with a non-type template parameter and a type parameter, but you can do this with function overloads. So here's an overload set, which is David. So several people in the audience laughing. Okay, so we pass in the arguments, and we say we call the function passing those arguments, and then we know whether it's a type or not. Okay, not bad. Except that we can't pass non-structural things as a template argument, right? So for string views here, this doesn't work yet. It works for ints, it works for ints, it works for types. It doesn't work for non-structural values. So let's make something we can pass as an NTTP. We're just going to make a from any type, which constructs from anything, and it converts to an int. Now in C++20 and later, you don't need to convert to int because from any is itself a structural type, which can be passed. But the implicit conversion to int means it works in 17 as well. So this is a class, it's not a template. So then we can say decl type of is type and pass it from any of var args. Everyone good with that? Well, now maybe you're wondering, like, from any of var args, how does that work? So from any of 42 is a value of type from any. From any of any old value is still a value of type from any constructed from that value. From any of int is a function type, taking an int, returning a from any, right? Because from any is not a template, it's a type. So this is, that piece of syntax ends up being a type if we pass it a type, and a template passable value if we pass it a value. So now we have what we want. We can detect these things. First problem, we got it solved. Next problem, we need to fill in these if const expr arms. The problem is they both need to be syntactically well formed. They're not going to be executed in both cases, but they both do need to be they need to be C++. They need to be good syntax. Well, we can use a similar trick. So running the first bit, when it's a type, we can use a similar trick to what we already used to get the type out. So we're specializing a typer so that when it sees a function type, it will extract that type T. Otherwise, it's just going to return void. But because we know that we're in the type half, we're never actually going to get to the void. We only need the part that returns the actual type. Yes?
Yes.
One side down, one side to go. So we've detected a type, we've grabbed it, we return the type identity. That side's fine. Well formed, everything's good. How are we going to get the value out? Remembering that we need the syntax in the second half also to be correct if it's a type. Even though it's never going to be called, it's going to have to be compiled. Well, if we do this, if vargs is a value, then this is an expression, it's a binary plus expression. If vargs is a type, this is a C-style cast of a unary plus expression. You like this one, don't you? Well, now, it's easy to make this well-formed in either case. All we need to do is make this special type with overloaded operators, and it's just going to throw away itself and return the T from the binary plus, which is what we want. We want to get the value out. And we don't even need to declare some of these functions because, again, this is in the value half of the if const expr. These functions are never going to actually happen. And now we are done. This is the macro, minus some const expr parts, but this is the part that does the type value stuff. Now we have, when we call cx value on any of these values, we get what we want out. And it all works nicely. So once again, thank you very much. And now I really am close to time, so I'll omit the other epilogue. But if you have any questions, we do have 1 minute. Yeah, Tobias.
If now somebody just passes in 42 without the CX value of macro, then it won't get as a const expr. So why didn't you turn it around? So to force the customer or to force the user to specify as a runtime password.
Why didn't I turn? Well, that's an exercise for the reader, but that would involve writing a variadic transform over a macro, I think, which is possible, but not with good syntax. All right, thanks, folks.